Okay, so I briefly go through what we did. I think we play a little bit about mathematics, and then to show you that to solve a boundary value problem, it is possible to use weighted residue method, and by using the shape function that fulfills the boundary conditions, then you can get the approximate solution. Okay, we show you one of the numerical example, and of course we also apply these linear shape functions or relative method to solve the triple cross problem or even these doubling equations. So this is the mathematical formulation that helps us to derive and solve the problem, which is not structured. 所以我们到目前为止，我们这个 Gatsby 有限研究的方法，它适用于所有的边界值问题，不仅仅是结构问题。我们花了一段时间来分析。And then, so we show you that even though you can make use of the Hooke's law, but you can also use the elasticity relationship and try to use the Gatsby finite element formulation to solve the problem. So this is what we have covered last week, and we show you that by trying to pre-multiply the governing equations and set it to 0, then we are able to write the force balance. 所以在我们应用这个 Gatsby function 的时候，我们是要把那个 governing equation 就是你们的这个二次不异常的二次微分项，然后要弄等于我们前面还特地存了一个加权函数，这加权函数基本上就是你们的形状函数 ，OK。然后为了迫使它等于0，然后我们利用这个叫integral by part， 把二次微分项 ，OK， 写成一个就是一个一次项对一个函数的积分，然后再把那个积分项变成是一个函数。Okay, so here we tell you about the use of this integral by parts to obtain the force balance equations by integrating the governing equation with respect to the shape function. Okay, so this is what we did. Okay, today we're going to continue the method by solving the preload problem. Okay, but before I apply that method, the residue method, I'll go through with you the common energy method. Okay, 所以之前这个 Gatsby method 我们是拿来找这个力平衡，可能大家都对力平衡相对熟，所以这个复杂的数学推出来跟最终力平衡得到的结果一样，大家会接受。然后，但是对于热应力的话，可能大家不熟，所以我就先给大家用这个复习一下热应力的问题。Okay, let's review what is the thermal stress problem before we try to extract the formulation. 我们在这个尝试用 weighted residue method 去解这个热应力问题之前，我们先用能量法来解这一题。OK， 假定你有一条这个杆，这条杆原长度为 L， 然后加热过后，它会有热膨胀，线性膨胀是原长度膨胀，热胀系数再乘上温升，然后后面你再给它一个拉力 ，OK， 所以这个时候，这个拉应力造成的这个额外的这个延长 ，OK， 最终会给你一个末端的总位，这总位含两个部分，一个部分是这个拉力造成的，一部分是热膨胀造成的。 Now consider a rod. Okay, this was cold with initial length M. Okay, when you heat it up, okay, then you get the thermal expansion. So the length of the heated rod is getting longer. So the amount of the thermal expansion is equal to your initial length at the lower temperatures times the thermal coefficient times the temperature rise. And alpha delta T is what you call thermal strength. We multiply with the initial length, then you got the thermal expansion. If you didn't stop there, because in this case, it could happen that the hot rod is further subjected to external force. So this external force, of course, by using the Hooke's law, you know that you're going to have the mechanical induced expansion, which is applied force divided by the so altogether, if a hot rod is subjected to temperature rise and is subjected to mechanical stress, then you're going to have a total expansion which consists of two parts. The first part coming from temperature rise, the second part coming from the applied force. Okay, so now we try to normalize that. Thermal strength, as we know about the free thermal expansions, when I say free, it's free for any force. Okay, it is defined as the expansions caused by the temperature rise divided by the initial length, and this thermal strength is alpha delta T. When you heat up the rod, and then when you apply mechanical force, and then you can obtain total strength, is defined as mechanical stress divided by Young modulus plus thermal strength. Okay, so this strength is the total strength. Okay, but the sigma over E is the mechanical strength. Okay, and this mechanical stress is then going to be expressed as Young modulus times the difference of the total strength and the thermal strength, and this will lead you to the mechanical induced strength. Okay, this also brings us to the point when you are calculating strain energy. Okay, you are talking about the mechanically induced strength, not thermal strength. Okay, so as a result, if you are going to write the energy stored in the rod, subjected to temperature rise, and subjected to the end forces, you're going to write the strength energy minus the external work done by external force. And this strength energy is your mechanical stress times the mechanical strength. Okay? The strength here, sigma, epsilon here is the total strength. So we should not bring the thermally induced strength be part of the strength energy definition. Okay? So now, okay, if you bring in the expression, what is sigma? Sigma is the mechanical strength times Young modulus. So this will lead you to the expressions. The elastic strain energy is half the integral of the Young modulus times the mechanical strength squared times the volume, and then that volume is going to be cross-sectional area times the length with the rod at a constant cross section. Okay. 所以我们在定义这个总的这个势能的时候，有两部分，一个是应力能，一个是外力做的功。然后你的应变能的话是机械应变能，所以它一定要把这个热制动的应变拿掉，所以你是应力乘上机械应变，然后应力就等于这个杨氏模式乘上机械应变。 所以乘出来的结果是你的杨氏模数乘上机械应变的平方，然后你把这个式子展开，你就得到我的这个应变能要求到的这个式子里面要积分的式子，它就是总应变平方减掉2倍总应变乘上热应变再加上热应变平方。所以 the definition of this strain energy, the final expression is going to be half the Young modulus times the volume integral of this expression. This expression is actually the total strength squared minus 2 times the strain times the thermally induced strain plus the thermally induced strain squared. Okay? So next, okay, what are we going to do? Next, okay, we're going to expand the expressions for the strain energy. So let's look at that. So that blocks it. So what we're going to expand is this expression. Okay. 好，我们看一下我们的总应变。How do you define the total strain? Okay. Total strain is obtained from the spatial derivative of the displacement. 还记得吗？我们如果说这个if you have a rod, okay, not 1, not 2, and it is undergo displacement u1, u2, okay, and okay, so this is chain over the length L, okay. So you can say the average strain is then u2 minus u1 over L. In the limiting case, where the length becomes very small, then your strain is going to be du dx. Okay? So here you can see the definition of the end displacement. Is it going to be caused by force or is it going to be caused by temperature rise? Okay? If this is caused by temperature rise, let's say temperature going up, and if this is caused by external force, okay? Okay? They are all together to cause these two total displacement. Okay? So when you define the displacement, you can define them using the shape functions. What kind of shape function you have? Okay? For displacement u1, you could have a shape function which is 1 at the point x equal to 0, 0. And for the second shape function, when x equal to L, this value 1 is going to be 0 at the end. How about the second shape function? The second shape function is going to be 1 at x equal to L. So this is u1 and then the shape function n2 to 1 here. But n2 is going to be 0 and x equal to 0. So this is the shape function we define to help us interpolate the displacement by using the displacement at the endpoint 1 and the displacement at the endpoint 2. Okay? So here, since it's going to be a total displacement caused by the temperature rise and caused by the external force, and of course the partial derivative of that displacement will then be the total strain. And this total strain is equal to the gradient of shape function with respect to the space times the displacement not 1, and then you have also contribution coming from the second shape function and not 2. So now we're going to expand the expressions and try to find the force balance. 好，我们接下来等一下会把这个式子展开，跟大家一起。Okay, let's try to write it. Okay. Okay, just now we have tell you the elastic energy is half Young molar times total strain energy square plus this is minus 2 times the total strain and thermal strain plus thermal strain square. Okay. Dx. Okay. And you also find the shape function. And you recall the strain is dn1 dx u1 plus dn2 dx u2. Okay? So you now try to substitute this in the expression. Okay, what's the expression here? Sigma square is basically, okay, the gradient square is gradient square plus 2 times the gradient of the first shape function and gradient of the second shape function. Okay, and u1, u2, and then plus the second gradient of the second shape function square, and then u2 square. Okay, so this is the first part. Okay, now we come into the second part. The second part is minus 2, the thermal strain. Okay, is then going to be simply multiplication of this. Okay, and then the last term, okay, is a constant square. Okay, that's fine. Okay, so after you have derived all this, now let's do integral. Okay, the whole idea is not just to look for the integral. The whole idea is, okay, remember your strain energy, your total appear in the total potential energy. So how do you eventually derive the force balance? As I told you, you have force 1, force 2, okay, associated with displacement u1, u2. The total potential energy you have is the strain energy minus work done, which is F1 u1 minus F2 u2. And the balance of the force can be obtained by derivative of the total potential energy with respect to displacement 1. Okay? And then you're going to have del UE, del U1 minus F1 times 1 minus F2 times 0. OK， 所以东西刚才讲，我们第一个是指是我们理解的，它是在节点以上的力平衡，所以它的这个总能量要拿去对这个该节点的位移做微分。So of course, so you only have the F1 left. So this F1 is then the partial differentiation of the strain energy with respect to displacement 1. Okay? Look at the expression here. Okay, anything is a function of displacement. It's all inside the expressions. And this, you have the square of the first term, okay? Then you can obtain as, okay, half the EA, the integral of, okay, these partial differentiations, which is the 2 times the shape function square, and then U1, okay, 2 times the first term. 我们现在做微分，我们微分是对谁微分？我们是对这个 U1 微分。 所以第一项是 U1 把微分过后就是两个 U1。So we first demonstrate the first term with respect to U1. So in the end, we have U1 squared become 2U1. Okay? And next we differentiate the second term. The second term which contains U1 is this. So then you have 2 times, okay, dn1 dx times dn1 dn2 dx times u2, okay? Because of your differentiation of u1, this becomes 1, okay? And then next we come to the last term. If you try to differentiate the last term with respect to u1, this is u2. So you have 0. Okay, 这个偏微分大家要学一下，就是说偏微分假设的是你位移1跟位移2是独立的变数。你如果对位移1做偏微分，就只有位移1项你能让它微分，位移2作为一个独立的变数，你位移2对位移1做偏微分，你得到0。OK。所以这里也是很重点的，就是说有限元的未知数虽然是位移场，不过每一个位移场，每个节点上的位移是独立的，你去解它 OK。Okay, so this tells you that the displacement at each node are independent of each other. So when you're doing solution, then you can solve it without a problem. But partial differentiation of next displacement with current displacement, we're going to give you 0. Okay, this is the first term. And then next, which else you can do partial differentiation. Okay, the part is now the second part. So this is the mechanical strength, total strength times the thermal strength. And where do you have the functions of displacement? So after differentiation, then you've got 2 dn1 dx times thermal strength. Okay, and then next, this term is let's say 0. And then the last term, which is independent of the displacement, u1, then differentiation again 0. So in the end, this total expression is going to be integrated with respect to the length. 所以看到没有，同学？你们通过这个总势能的微分，然后就得到总势能的微分要0的话，这就是一个立体的方程，就是应变能对位移场的微分，再减掉力，就节点1上面的力。同理，你如果要做这个 u2 的微分也可以。So you do now apply the same method to u2. Okay, let's see what the expression. Okay, let's. Okay, for the same expression, you can also do differentiation with respect to normal displacement too. 所以刚才对节点1微分我们现在对节点2的位移微分 ，OK。OK， 所以最终得到的节点2上面的力。就等于你应变能对你这个位移2的微分。So now you can do the same to find out the normal form balance that is not true. And in the end, you're going to do the differentiation of the expression here. in this case, which are the functions of u2? I circle it down. Okay, this is the function of u2. You only need to differentiate this term because all other are 0. So in the end, you have 2 the n1 dx, the n2 dx. Okay, times after differentiation of u2, then it becomes 1. So then you have u1 left. And then the second term is going to have 2 the n2 dx squared, and then u2. And then the third term is then left with minus 2, and then this the n2 dx, and then this is becoming sigma t. And then you're going to integrate with respect to the length. 好，所以我们现在已经把这个两个节点的力都找出来了。So we have found out the normal clause. Okay. Now we're going to write them as two force balance equations. Okay, here, so the first equation is what? Okay, so because every term here got 2 inside, so I can take out it, so it's going to be EA. Okay, and then this is going to have the integral of this gradient of shape function 1 squared times u1 plus 2. Now after factoring out 2, there are no more 2. Then you're going to left with the gradient of shape function 1 times the gradient of shape function 2. Okay? And u2. Okay? And then minus, okay, minus, I put it in red color. Okay? Put it in red, the n1, the x1, t, and then integrate with integral dx. Okay. So here, okay, what am I going to do? Okay, look at here. I only have first term and second term dependent on the displacement. But the third term independent on the displacement. So now I can say I can treat that term as a fourth term. 我把最后一项把它视为什么？把它视为一个力的项。This is then the n1 dx epsilon t dx. Okay, and then what's next? And then what's next is then the expression here, which is dependent on the displacement. Okay. So you see now, this is what we call external force. Okay? And what is this? Okay? This is the n1 dx. Remember the shape function? This is x equal to 0 and this is x equal to m. The first shape function is 1 minus x over m. And then the gradient of that will then be minus Okay? Next questions? EA over L minus times L minus 0. So in the end, you have the minus EA. 看到没有？所以你这一项，按alpha delta。So this term, in the end, can be expressed as negative alpha delta. Okay, and then this one, we don't expand it yet. Okay, so of course you can do. So if you want to expand, this is what? N1 squared. This is minus 1 squared. Okay, and this one over L squared. Second term, minus 1 L and 1 over L. 我们看到的这个式子应该可以简化了。So now you can write your force expression and then minus EA epsilon T. So this is telling you external force minus the thermally induced force. Okay? 这个是热应变。乘上两次魔术就是热应力，再乘上节电机就是热自动力。Okay, and then the expression here is then going to be integral of 1 over L squared, and then do 1 minus 1 over L squared, and then U2 with respect to dx. Okay? And of course, after doing the integration, this expression is going to be EA over L, and then do 1 minus U2. Okay? So this is how we obtain the first force balance. Okay, look at the expression here. So we also identify the not two force balance. Left hand side is the external force. Right hand side got a lot of expression, but among one of them is the expression. Okay? So if you now write them, you're going to write them as the same expression, but it's now the gradient of the circumference. And then this one, because the gradient here is this is n2, and x equal to 0, this is 0, and x equal to f, this is 1. So this shape must be equal to x over f. So your gradient of the shape function is then going to be 1 over f. So this expression is 1 over f. And then after you do the integration, okay, this will then be times x, and the x start from 0 x to f. So the expression here will then give you what? Will then give you E A 1 over L times L. So this is now positive 1 times epsilon T. So this term is then your external force. How about the second term? Okay, the second term on the right hand side, we can write it here. So the other term is here. This is the EA del n2 del x squared, and then u2. Okay? And then integral with respect to dx. So that's the right hand side. Okay? So let's see. So let's now do the equation. Okay, this one, I should tell you, this is minus 1 over L. This one is 1 over L. Okay? So the expression here is EA minus 1 over L squared U1 plus 1 over L squared U2 and integrate with respect to x. X change from 0 to x change to L. So the expression here is EA and then over L, and then you have the expression minus U1 plus U2. So in the end, your expression here is now going to be external force plus thermally induced force is equal to EA over L minus U1 plus U2. OK？ 所以我们接着把这两个方程式写下来。So let's summarize the equation. Okay, I think I got it. From here, this is the f2. Okay, for the first equation, you have f1 minus EA epsilon t is equal to the EA over L, and then U1 minus U2. And then the second equation is minus EA alpha delta T is EA over L minus U1 plus U2. So this is equation 1, equation 2. 我们对到现在是有两个力，一个是节点上节点1上面的力，一个是节点2上面的力。然后我们现在把这个式子写成比较的。So you will now write the force as a force vector, and then you now have the left hand side to be other than force vector, you now have the thermally induced force vector. And then the right hand side, now we have the EA over L. So you have the matrix times the rotation factor. So this is U1, U2, U1, U1, and then next you have the minus U1, U2, then you have minus 1, 1. In this way, you realize that your force balance is going to have an external force, okay, plus thermally induced force. And then the right hand side is the elastic force. So 你们对到现在，这形象上要怎么理解呢？我们来看一下。 and force 2. Then you have displacement U1 and U2. You can write the equation as this EA over L 1 minus 1 minus 1 1 and displacement U1 U2 equal to external force F1 F2. Okay? So this is the elastic force is equal to your external force. Okay? However, if you now start heating up the system, okay? So what happens? Supposedly, if you do not do anything, if you do not constrain it, being heated up will cause a thermal strain, which is the thermal coefficient and temperature rise. Then eventually, this thermal strain has the initial length. Okay, so they give you the thermal expansion. Okay, so what is effect by heating? If you are doing the heating, this length is increasing. So what is causing the rod to increase? It is caused by an equivalent extension force. So this extension force is what we call E A epsilon T. Push, in order to extend the rod, the right hand side must have the right force pulling it. The left hand side must have the left force pulling it. 看到没有？你如果因为加热有额外的热膨胀 ，OK， 这个热膨胀是把这个整个长度拉长。什么力会把这个长度拉长呢？一定是张力 ，OK， 张力在右手边是向右的，在左手边是向左的。但是我们定义 x 的方向为正 ，because we define the force in the x direction is positive, but for tension, okay, the knot 2 is subject to EA epsilon T, which is in the same direction as x. But at knot 1, the force is going to be minus EA alpha delta T. Okay? So in that way, so this expression here is what you call thermally induced tension. Okay? 就是我们推的公式有点复杂，按照那样的方式去推。但你最终得到的结果，你要理解它的物理意义。OK， 一根不改 ，OK， 你去拉长它，它会有伸长的问题。然后你去加热它，它也会伸长。那个加热的效果是什么？加热的效果是等张力再把它拉长。所以等张力是什么？右手边 EA alpha delta T，EA epsilon delta T， 然后右边呢是负 EA epsilon delta T。所以这个就是热膨胀的效果。So the effect on heating and temperature rise and thermal expansion is equivalent to applying a thermally induced tension on the two knots. Okay? Okay, so this is easy because you have two ends. If you now have more expression, then it's going to be more complex. Okay, let's see what we have derived so far. Okay, we start from the expression for the strain energy. We expand it into the component of mechanical strain, total total strength and the thermal strength. And then eventually, next we apply the force balance by taking the derivative with respect to displacement U1. And then next we do the same. The force balance at log 2 is going to be the strength energy, the derivative of the strength energy with respect to U2. So this will give you then the expression here. So eventually, you express this. Left hand side is the elastic force, right hand side is external force plus thermally induced tension. And if you go substituting the shape function in, then you're going to obtain, okay, this thermally induced tension is -1 on the left hand side and 1 on the right, -1 on the left hand side and 1 on the right hand side. Okay. 所以它的这个方向很简单，你只要画得出它是这个是张力 ，OK， 那就对了。And in summary, you can express your matrix operations into this matrix vector form. Okay, so how do you define the elastic strength energy? It's basically the straight function gradient matrix times the displacement vector minus the thermal strength. And how about the thermal strength? It's just the free multiplication of the elastic strength with respect to the Young modulus. And next you can find the elastic strain energy per volume. And now you have the expression here. This can be expanded as half the Young modulus times transpose of the displacement times the gradient of shape function matrix minus the thermal strength and multiply the shape function gradient times displacement vector minus the thermal strength. And then next you can further do the expansion. Okay, by substituting the volume integral. Okay, then you can. It's a complex form. We didn't need to expand it. But next we have to take the partial differentiation with respect to the displacement 1. Then we start calculating any term that is depending on the displacement. Of course, there is only axis in the displacement vector. The partial differentiation will give you one of the two terms in the end. Then you got your V matrix, transpose and V matrix, and displacement U1, U2 is then going to be the external force. So this is our derivation for the thermal stress problem. Okay, it's a little bit heavy here, so probably we have a break for 10 minutes, and then we're coming back again using versatility method. 对这个正应力的问题，形象来讲，就是你之前的这个力平衡，这个内力平衡跟外力平衡，再加上热造成的这个张力 ，OK， 就是这样。等一下我们会再回过头来用这个维特加权这个残余方法来有这样的一个力平衡方法。Okay, we'll take a short break of 10 minutes, then we'll come back at 2:25. Okay, thank you.
敲个底，然后敲出这个点，它应该是那个，它应该是这个方法，而不是一开始就敲这个面，它有其他东西。你自己看这个旁边的那个。就是那个 R 就 X， 你知道吗？哦，你那个微分方式反复翻到 R X， 开始强调，然后就你因为你那个分换乘上去，乘上它，然后变成
就说是一个点，它里可能是零，然后我们外面还是零。
我不想是这样，
因为两边的。
现在那个
相加等于零，那就是它好像等于零3点还是3点？
我觉得是啊，
对，它是这样弄吗？
对吧？我觉得是这样。
而且还有，我现在开始，
感觉你是不是有这个？
derive using energy method. Now we're going to derive it using the Method-2022 method. Okay, as I put it before, I think we now have a very clear idea about what is stress, and what is strain, and then next, we're now going to get the governing equation of the rock subjected to temperature rise. 好，我们来先看一下，如果说你有一个杆 ，OK， 它受力，左边右边的受力 ，OK， 的应力 ，OK， 在 x 这边，然后在 x 加比 x 这里 ，OK， 它的受力都为西马 x， 然后这个是西马 x 加比 x， 西马 x 加比 x， 这边表示为西马 x 加上西马比 x 加上比 x。So now we try to derive the governing equation for a rock subjected to not just force but also subjected to temperature rise. Okay? But here we start from the case of the load distribution. So you can see that because of the stress distribution is different. So the right hand side would have more stress than the left hand side. So you can now take the force balance. Okay? Okay? Both sides must be multiplied by the area. Okay? Now we come to the force balance of the rod. Okay, the force balance of the rod tell you, okay, this force balance, okay, sum of the force is equal to mass times acceleration. In the case of no acceleration, the right hand side must be 0. So this expression can then be minus sigma A plus sigma A plus d sigma dx dx A, okay, equal to 0. Okay, so then after cancelling the minus sigma A and sigma A, then we have the governing equation of d sigma dx, okay, is equal to 0. Okay, but in this case, you recall what is sigma. Okay, sigma, okay, is F over A. Okay, is in the case of mechanical induced stress. But if you heat it up, you extend more. Okay, so this expression can now be expressed as Young modulus times total strain minus the load strain. Okay? So if you bring the expression of the strain inside the expression here, 好，我们现在写这个力体呢，基本上是用牛顿第一定律，左边力减右边的力 ，OK， 然后就等于零加速。然后左边力是应力乘上截面积，右边力也是应力乘上截面积，不过两者之间应力就差了一个这个一次项，然后这个一次项是应力对这个长度或密度一分 ，OK， 所以I rewrite the expression here. So this is governing equation, okay, in terms of the stress. But as we learned before, we are more confident in the strain. Okay? So the stress is mechanical stress. Okay? It must be the modulus times total strain minus the mole strain. And what is this total strain? This total strain is du dx minus delta t. you now substitute this expression into a verb, what do you have? d sigma dx is now e second order derivative of the displacement field with respect to the spatial coordinate minus the epsilon t dx. Okay? So you come to the point now. Okay. So you see here, here being the governing equation, you are talking about second order derivative of displacement, okay, minus the strain gradient equal to the right hand side equal to 0. But for most of the finite element formulations, you assume thermal strength is constant within the rod. OK， 所以在这个简单的有限面前，就好像我们假设位移场是线性变化，所以应变是一个常数。OK， 然后如果受热，我们也假设在有限元素里面，它单元或者元素的受热温度是在空间上一起受热，所以在空间场上，你的应变不存在变化。OK， 所以这就是我们简单的有限元素的假设。So in this formulation, you see that we're going to assume thermal strength within the finite element, or this truss element, is going to be constant. Okay, it's because that truss is subjected to uniform temperature rise. Okay, so the thermal strength is going to be constant throughout the length of the truss. So as such, when you take the gradient of that thermal gradient along the length, along the space, that gradient is going to be 0. Okay, as such, so your governing equation remains the same as for the rod not subjected to temperature rise. Okay, on the assumption there is 0 thermal strength gradient. Okay, 所以有些元素其实做了很多假设。你如果说单纯看一个元素去计算，它是一个非常差的一个近似体。OK， 但是因为你划分它很多个元素，所以你在每个元素里面，温度场是固定的，是一个常数，所以你的这个热应变不会随空间的改变。OK， 所以你的可以极大的去简化它的这个算法。Okay, so now, before we try to solve it, let's introduce you some idea about the thermal expansion. This, if one end is fixed, the other is free. When you heat it up, you're going to have free thermal expansion. U2 is equal to alpha delta T times the initial length. In the next case, you're going to have block force or block stress. If not, you have the same rod, but both ends is fixed. So total mechanical strength is 0. But then this total strength is coming in two parts. The first part is the mechanical stress. The second part is the thermally induced strength. So these two must be added up to become 0. As a result, if the end is blocked, the thermal stress is then going to be minus the thermally induced stress. 我们现在介绍两个概念，一个就是一根杆，一边固定，另外一边不受约束。受热的时候，不受约束的这个末端会做自由的热膨胀。第二个情况是两边都受到约束，所以你的长度是等长。在这个情况底下，这个产生的这个反重力或者是这个热应力 ，OK， 怎么跟你的造成同样的应变呢？所以你的机械这个内应力刚好要跟你的热应力相抵消，正负号相抵，所以消减下来，有总应变为零。 some idea. And then next, now we start going to derive the thermoelastic strength. Okay. So let's recall how do we derive that. Okay. Okay, let's derive that. Okay, now we're going to derive using the method. 好，我们现在用这个加权这个单一法来计算。So how do you solve the problem? Okay. So we are going to use the weighted residue method. So what is weighted residue method? If you recall, weighted residue method is integral of the shape function times the second order differential equation. And then set it to be 0. So this is your weighted residue method. So you can choose shape function 1 and shape function 2 for the blocks. And remember, the shape function it will be n1, it will be n2. So this is the two shape function. Okay, we realize that it's difficult to derive. Okay, and now we start in the expression there. What is the expression there? The expression here is second order derivative of this is going to be 0, assuming no normal strength. Okay. Okay. Now, how do we derive this? Okay. Now, okay, because we have this 0 term here. So we can rewrite this is my ni second order derivative, second order derivative displacement over the directly over the space. Not in any length. Okay. As we mentioned before, if this is the shape function, then the gradient here is negative 1 over L. And then shape function 2 is positive 1 over L. Okay? This is your so I'm going to have a constant for my gradient. Does it mean that I'm going to have 0 for this governing equation, which is second order derivative of my displacement over the space? Okay? So I'm not going to handle this because this second order derivative is definitely going to be 0. Remember, u is equal to n1 u1 plus n2 u2. Your derivative with respect to the space is dn1 dx u1 plus dn2 dx u2. And second order derivative of the displacement over the space is then going to be second order derivative of the shape function u1. Second order derivative of the shape function and u2. So this term is for sure 0. Okay? So integrations of this got no limits. Okay? So what can I do? If I'm going to do integration, as for approximation, I can write this as n I x, and this together. And by doing integration by parts, okay? So integration by parts. How to do integration by parts? Integration by parts is done by doing a swap. Okay? This swap is shape function times du dx minus what? If you do the swap, then you're going to have du dx and dni. Okay? Because this dni you can write them as dni dx and dx. So this is now my new expression. Okay? dni dx and dx. Okay?所以这个概念是什么 ？integration by parts 的概念，基本上就是what do we integration by parts? Okay, the idea is if you have difficulty integrating this, okay, you should not have problem integrating the other part. Okay. 所以大家看懂吗？这个是一个方块 ，OK。So what is integration? Okay. Let's take a square. Okay. Okay. Do you have problem integrating this? Okay, so this is integration of x squared dx, where y is equal to x squared. Okay. So if you now can do the swap, okay. So what is swap? This is swapping of the area. Okay, if now y dx. Then what do you solve? You solve it to be yx minus x dy. Okay. 所以形象上，你这个 integration by parts 基本上是就是这个做法，基本上是找完这个总面积。再减掉这个横向面积，我就得到了我这个。So whichever you learn from your calculus, you don't need to remember formula, but you need to remember the meanings. Okay, then you will not forget it. Okay, by doing this, our integration by parts are giving you a good approximate of second order derivative. The integral of second order derivative. We now often it to become first order derivative. You are not going to have zero. Okay, 所以基于这样的方式 ，OK， 我们就可以再继续这个下一步的推。So, okay. So let's see how do you apply this to your this equation. formulation can be written in this form. Okay. Now I'm going to apply this to my thermal stress problem. What is my thermal stress problem? My thermal stress problem is about the same. Okay? Except that the total strength, which is du dt, du dx, coming from two parts. Okay? One part is mechanical stress, induced strength, but the other part is the alpha delta T. Okay? So look at my equation there. Okay? My equation there, these two terms, okay, is going to be balanced. Okay? What is the balance here? It's going to be E A N I du dx from x equal to 0 to x equal to L is then going to be balanced by E A, okay, du dx times dn dx times dx from x equal to 0 to x equal to L。好，我们来看一下我们这个式子。这个式子基本上告诉你，这个你的这个叫equation by part，左手边跟右手边的式子 ，OK。这个式子是什么 ？What is E A du dx? Okay. If you not imagine you are taking I is equal to 1, N1 is 1 and x equal to 0. But N1 is going to be 0 and x equal to L. Okay? So if you now substitute these into the shape function, okay, du dx at x equal to 0, okay, it's going to be E A N1 x equal to L times du dx at x equal to L minus E A N2 x equal to 0 and du dx x equal to 0。所以你这个，如果你代入的是 N1，你去代，然后把那个边界值带进来，你会发现，哎，我这个 N1是正，是零啊。然后我的这个 N1 在这里是1啊。OK。看到没有？所以这个式子呢，你带入 N1 的话，你得到的是节点一上面的力。So what this force is? Okay, your EA du dx. What is your du dx? Your du dx is here. Okay. Your expression here is your this minus EA times sigma E, okay, plus alpha delta, okay, and this is your expression. So the left hand side of your expression here is what? your mechanical force. Okay? And second term is this minus what we call EA alpha delta T. And this is your thermally induced force. 这个旁边这个积分可能大家不熟，但是你带进来后，会发现它这个力本身是。Okay, then we continue the same on the right hand side. So remember, just now I was integrating these to shape function 1. Because all about shape function 2. Shape function 2 is F over L. Okay? So if I now expanding this is going to be EA N2 x equal L del U del x at x equal to L and then minus EA okay, N2 x equal to 0 and du dx at x equal to 0. Okay? So from the expression here you see it can only be 1 at x equal to L. Now it's 1. Okay? But the other term is going to be 0. Okay? So your now remaining term is EA times 1 du dx at x equal to L. And then if you now substitute the expression here, this is then going to be sigma over E plus alpha delta T. So now your expression here is EA, okay, sigma over E plus EA alpha delta T. Then you now have your stress as the area plus EA alpha delta T. So from here you can see, 如果你单纯只是看你的内应力部分，你的这个元素的左手边 ，OK， 你这个热产生的这个力是一个张力项，它方向刚好是相反，一个是正，一个是负的。然后这边你也可能会问，哎，我这个直接应力是怎么直接应力不用反正不管是正的是负的，它就是 F1 F2，OK， 方向会自己自带 ，OK， 自带方向。So this is how you handle the left hand side. And then next, how are you going to do the right hand side? Let's see how you handle the right hand side. The right hand side we previously derived. Now I copy it again. Okay, so let's see. This is the right hand side. Okay, the right hand side is EA. Okay, del u del x times dni dx. Okay. So I have this right hand side here, right? This is my right hand side. Okay. So if you do the expansion of this, my right hand side is dA, and then this is dn1 dx u1 plus dn2 dx u2 and dn9 dx dx. So if you now complete the term, okay, for ni is equal to n1, what do you have? You have your force 1 minus EA alpha delta is going to be EA, and then you have dn1 dx squared plus dn1 dx dn2 u2, okay, and integrate the whole thing with respect to dn. 所以你这个节点 D 上面的地平衡基本上是 F1 减掉 alpha EA alpha delta D， 然后右手下是你的内力或弹力，然后 alpha 的 Ni equal to F2. If you write that, then you're going to have F2 plus EA alpha delta T. The whole expression is going to be EA integral of dn1 dx dn2 dx u2 u1 plus dn2 dx square u2 dx. OK， 这就跟刚才得到的解释是一样的。我们一般不能处理的是这个这样，我这个给它带入是 x1 全部带入形状函数 v 的斜率函数一律带入 x 等于 l 都带入。So this brings us to the point that weighted residue method is a generalized version of finite element formulation. So long as you have defined the governing equations, so now you can solve it and apply the boundary value, and then you solve the answer. So this is similar to what we did with the energy method. By energy method, we rely on our structural energy idea. We now have no idea about the thermal or temperature field, so then you can derive it from the governing equations. OK， 我们结构力学我们有这个势能应变能的方法去求有限元素法。OK， 但是你在这个温度场的情况底下，你的能量怎么定义呢？或者在流场或者速度场，仅剩于是静电场、磁场，所以你还是可以通过这个叫做这个 weighted residue 加权这个 residue 叫什么？残余吗？还是 residue 加权残余法 ？OK， 去修解。Okay, so that's the idea, and then now we come to our PowerPoint to complete the story. force must be equal to external force plus the thermally induced tension. This tension is going to be outward positive. Okay? So this is going to be toward the right on the right hand side, toward the left on the left hand side. So this is then a tension. 所以你最终得到的结果是什么？是一个两个节点的这个感，它两个节点上的力平衡。首先是弹力要等于外力，再加上热制动造成的张力。张力在右手边是右向的，左手边是左向的。但是因为我们定义上这符号都是就是 x 方向为正，所以这个左向的这个张力是变成负张力。Okay? So this is then simple obtain. Then next, of course, the problem could be more complex if you now have the body force. Okay, because of the presence of the body force, the Gaussian equation is no more zero. Okay, the stress gradient is no more zero. It's then going to have stress gradient plus the body force, body pressure, body force divided by the cross-sectional area. Then this is going to be zero. 如果说你要去把这个问题再扩展，你还可以去解决这个 body force 的问题。So this brings us to the point is when you start using the 3D truss element, you'll be asked for normal force, you'll be asked for temperature rise, you will also be asked for body force. Okay, the formulation is different. In the case of temperature rise, you assume constant temperature. There are no thermal strength gradient. Okay, but in the case of body force, okay, other than the stress gradient, you have a non-zero body force term. Okay, so then we're going to have different formulas. But today we're not going to study this, and then we're going to start on the exercise on thermal stress problem. So in this exercise, now you have a two rod element, okay, and then it's subjected to uniform temperature rise, 10 degrees Celsius. Would you be able to determine the reaction of this rod, given the rod made of the material like this? Okay, 这题目特别简单，为什么？是让你去验证，即便你不懂有限原理，请问一根杆增加10度 ，OK？ 请问它的这个热的这个热，我们要找的是反作用力是多少？这基本上是 drop force。How to determine the drop force for due to the thermal expansion? Okay? We find out that it's simply imagine now you have a rod. Okay? You heat it up, you get lengthen. This lengthening is upper delta LT. And then now you want to apply the force to push it back. Okay? You push back the hot rod by this amount. Do you know how much the mechanical force for keeping the length the same? To keep the length the same, okay, the mechanical force you have to apply is then your EA, okay, epsilon T. And what is epsilon T? Is alpha delta T. Okay? 可以看到的，这个叫 block force。不管你的这个杆是长是短，不管你的杆是分1节2节，所以它的这个 reaction force，OK， 基本上是EA alpha delta T，OK， so if you go do analysis, supposedly we're going to have this analytical solution. So this is what ANSYS verification manual is listing. Okay, so whenever people come up with finite element simulation, the first thing they do is are there any analytical solution? Yes, we have. The next thing is they do the calculation. It's a calculation, give you a numerical answer which is close to that. If yes, then it's perfect. So if not, you have to keep dividing the element number until the point that the solution is converging to the analytical solution. If they are not converging, then your formulation is wrong. So finite element is a simulator. Okay, that has been verified. Okay, but you have to use it with cautions. Okay, this is a numerical method. It's not an analytical formula. Okay, so it may not be right. 所以有些人做的应用啊，你要假定它是错的，然后你要去验证，验证完对了才可以用。OK， 所以有些元素一般来讲，用在航太企业，它都是做完很多实验，验证过模型，然后才采用。如果说你用的材料没有测试过，没有模拟过，你就直接去用，你要假定有些元素算出来是错的。Okay, so you have to be cautious whenever you use finite element simulation. Okay, it now becomes a tool for even solid work. But after the simulations, you have to be careful. So it may just give you the trend. The number could be wrong. Okay, so don't just believe finite element simulation even though I'm teaching it. Okay, so ever since I'm simulating the rubber, I realized that it could be one of the difference. And ever since, if you do math, if the material is subjected to thermal pre-stress, any pre-stress will make your structural stiffen, and then your simulation will also be different. 好，我们来看一个分解。How to solve the problem? Okay, so here you have two elements, three not one, not two, not three. So where is the end point? The end point is on the knot 1, they are going to be force 1, F1. Knot 3, they are going to be end force 3. At the middle of the rod, there are no external force applied. So the force 2 is 0. All the force direction is defined along the x direction. So it's positive x. Okay? So next, how do you solve this? To solve this, okay, I prefer you reading the physical meaning. Elastic force balance is going to be equal to my external force plus thermally induced tension. So for element 1, it's only subjected to force 1 and force 2. So force 1 is non-zero, force 2 is 0. How about the tension on element 1? Along the x direction, on the right hand side is positive tension. On the left hand side is negative tension. Okay, negative force to be positive tension. Okay. So as such, now you have the force balance for element 1. And then next, you have the force balance for element 2. This is the elastic force, EA over L. In this case, the length of the rod is half the full length. Okay, so EA over L over 2. And then have this component, and then you want the left knot is U2, right knot is U3. Okay, so you have to write the elastic force is equal to the external force. External force is what? Knot 2 is 0, knot 3 is non-zero. Okay, together you do it a sum. Okay. So this will give you the force sum. Okay, by right, it should be written whatever force there. Finally, the external force is F1 non-zero, F3 non-zero, F2 0. And then for the internal elastic thermally induced tension, this one is minus EA alpha, minus EA epsilon delta T. This is positive EA epsilon delta T. Then on the other side, the thermally induced tension is for the second knot is minus EA epsilon delta T. For the third knot is EA epsilon delta T. when you do the summing, you see that thermally induced force is only present on the boundary. 所以你看到没有？你最后看得到你的热应力或者热力的，只存在边界，因为你中间位置左元素的热应力跟右元素的热应力刚好相抵消。OK， 热应力最终只存在边界。So now you add up, then you got the total force coming from the reaction force and also coming from the thermally induced tension. That thermally induced tension is only present on the boundary. They are zero within the body itself. And then they are going to balance out with your elastic forces. Okay. So now you have the expression here. So this is the force balance at 3 knots. So now you have written it down, 3 equations. How to do the solving for 3 unformed? Okay, in this case, because U1 is both ends is fixed, U1, U3 is fixed. Now you can make use of the equation 2. Okay, equation 2. This is EA. This is the stiffness constant and minus 1 plus 2 minus 1. So in the end, it's the stiffness times 2 times U2 is now going to be 0 force. So U2 is subjected to 0 displacement. And then from that 0 displacement, you substitute into equation 1 and equation 2. And finally, you can find out the reaction force. It's going to be EA epsilon delta T. One is negative and the other is positive. So in that way, you can find it out. Okay. 好，这一题相对简单，只是给大家一个练习。So this is a relative simple question for exercise, so that you realize that hey, I know my block force. Okay, this block force is identical to what I derived by means of finite formulation. Okay, and then next you have this problem. Okay, this problem is more complex. Okay, I think you should have it in your exercise. Then I'm not going there. Okay, so this problem has one thrust being heated and the other thrust not heated. So by doing the force sum, then you are going to have force balance. By solving the force balance equation, then you are going to find out the displacement U3. Okay, so that's the whole idea. 所以我们现在讲的都是力平衡，所以跟大部分课本的讲法不一样。大部分课本，他每次跟你说他是什么，你的那个干部矩阵要组合啊，说那种组合就没有任何物理意义。说起来组合，其实你在做的其实是把各个节点的力加总在一起。OK， 所以这个才是实际的有物理意义的一个解释方式。OK。Okay, so now we proceed to the next, the last part of the experiment. So now we are coming to the space thrust. So you have learned about the 2D thrust. And even when you have your NC session, you know that the thrust you define is 3D spark. Okay, you have to define that in the z direction, all the displacement is 0, so that you can measure 3D spark into 2D spark. Okay, now let's analyze how 3D spark has to be formulated. 我们先看一下这个立体的感单元是怎么存在的。Okay, as you know, a simple triangle will make a stable structure in the 2D plane. Okay, but this is not stable in the 3D space. It can up and down. Okay, and then the next question is, what is the most simple stable structure? Okay, Here you have a rectangular base and then four trusses joined together at the point. Okay, so this is a stable structure. Okay, but the simplest stable structure is tetrahedron. What is tetrahedron? Tetra 是什么意思？一二三四 ，hedron 面，所以你这个是四面体，这个底下一个面，边上三个面，这个四面体是最稳定的结构。Okay, you might not know tetrahedron, but tetrahedron has been the simplest stable space truss. How many truss elements you have? You go and count at the base you have 1, 2, 3. 3 trusses. At the top you have 1, 2, 3. Altogether you have 6 truss elements. How many joints you have? 1, 2, 3, 4. 所以你有四个节点，6根杆。So who is using that? Of course, you might have seen the structure there, but the earliest report of that was by Bell. Who is the Bell? It's the Bell Graham. 那发明电报的这个贝尔实验室很出名。OK， 这贝尔是做通讯的，他也要做这个航太。那时候他做航太，这个莱特兄弟还没飞上天，他就想到，这个放风筝嘛，一个风筝不够，我们只做2个、3个组合起来，这样不是可以载重的嘛？所以 the day when Wright brother haven't invented the aeroplane, Bell, being the inventor of the telecommunications, tried to make aircraft as well. So he has engages his engineer to come out the tetrahedral cracks. So that's a view how the tetrahedral crack looks like. 我们看一下这个四面体风筝是怎样。虽然它是四面体，不过它是有2个面有子公主。So this is a 64 units of the tetrahedral type. You can imagine the top being 1 assembly, the bottom of 3 assembly. So under the wing, you can fly like a kite. This type can fly. Yeah, it's stable. The idea is stability. Yeah, and also it can stack up. If you have one single diamond type, you cannot stack up. But this one tetrahedral can scale up easily. And the reason why it's good is because it's the simplest stable structure. So you make use of the least material to make a structure.
Makes the most.
Yeah, the lightest. Yeah. That's the main motivation. Yeah. Okay, next we review how do we make the tetrahedral type. Okay, so a short video as well. you can make use of some straw, cut it into equal length, and then you have the cable. Okay. This is also showing you what the truss element means. Okay. It's a bar with the end fixed. Okay, but which is free to rotate. They are hinged together. Now you have two triangles. Now you make the third piece. Then you have the tetrahedron. So you see, it's cable pull to maintain their tension and one pieces. Okay. One unit of tetrahedron have two surface, two plane made of paper. Structure wise is tetrahedron, but the surface wise is two plane. Okay. 它虽然是一个这个是叫三角锥嘛 ，OK， 但是它只有两个面有贴纸。So you repeat to make 4 units. Okay. Then you can make a bigger triangle cube. Yeah. Okay, so after the interesting part about height, now we come to the mathematical part about how would you model a space truss. Okay, so one of the issues of the space truss is what is the orientation. Okay, I think defining a space truss is easy. You basically have knot 1 and knot 2. Okay, how to define knot 1 and knot 2? First, by the normal coordinate x1, y1, z1. X in this axis, y in the other axis. Okay, I will put it there. See you there. Okay. So that's for knot 1. Knot 1 coordinate, knot 2 coordinate. And then, how do you define the length of the truss? The length of the truss can be obtained by Pythagoras theorem. You just take the projected length along the x-axis, square it, plus projected length along the y-axis, square it, and projected length along the z-axis. Okay, 如果同学看不清 ，OK， 画一下。当然，最理想是你到时候回去做一个三角锥，然后看着是角锥的这个边。So you now have this coordinate, and along the plane you have end point here, and next. Another end point. Now these two define one linkage of length M. And how do you find the length here? Okay. To find the length here, if you see the projection. Okay, 你如果看投影的话，这个是你的头，在 x 方向的投影。So here define you x1, x2. length when you view this， 看你的这个手投影，这个是投影的长度，但是你斜一边，你投影长度会变回来。OK， 所以我们讲投影的长度。OK， 如果这个是 x plane，OK， 这投影的长度就是我直接到我手臂，这个叫 x。OK， 所以这个是其中一个部分。然后现在我们打光，如果说另外一面光打在一个垂直面上 ，OK， 打在一个垂直面上 ，OK。If you now try to define, if you shine the light and try to project this onto the plane here, you see here. So this is now the projected height difference. This height difference is y2 minus y1. This length difference is x2 minus x1. And then next, of course, you can project it in onto the z plane. Okay, by shining the light from the other side. This projection will give you, oh, this is the z length here, and here this is my z length here. So these are the projected length. So by taking the three projected length in the x plane, in the plane along the x-axis, along the y-axis, along the z-axis, now you've got the projected component, and then you square it and take the sum of them and then take the square root, then you're going to have the total equivalent length of these three troughs. Okay? So this is definition of straight trough with two knots and the length definition. Okay? But question here is, how about the direction of the trough? Okay? So as you can see, my arm is fixed in length. So if I'm now doing a turn with respect to the lighting, you can see the projected length is different. Okay? If I now define this x-axis and y-axis using my hand, okay, you can see that